Okay, another problem here, problem number 5 on fatigue, on designing against fatigue. It says a notch-free circular shaft is to be subjected to an alternating torque varying from 1800 to 2300 Newton meter. So the minimum value for the torque is given as 1800 and the maximum value of the torque is given as 2300 Newton meter. The shaft is to be made of hot rolled wrought steel, which has a yield strength in tension of 242 megapascal. So this is the yield strength of the material, and endurance strength of the material is 152 megapascal. So the yield strength based on uniaxial tension test is given 242. And the endurance strength is given as well as 152 megapascal. In this case, it says determine a suitable diameter for a factor of safety of 2. So the factor of safety is given as well as 2. So minimum torque is given, maximum torque is given, yield strength of the material, endurance strength are given, factor of safety is given. And we don't have any notches here. It's a notch-free shaft, so we can consider KF as one. These are the values that are given, as I said, and then we have to find the diameter of the shaft. So the first point is to calculate the mean and the reverse torque values. So the mean torque value is the maximum plus the minimum over 2. So the maximum was 2300. The minimum was 1800 divided by 2. This gives us 2050 Newton meter. The reverse torque is the maximum minus the minimum over 2. So the maximum is 2300. The minimum is 1800. So this value minus this value over 2 gives us 250. So these are the two values that we require at the moment, the mean value and the reverse value. So the shaft here is subjected to torque or torsional moment. So the torque here and the polar moment of inertia J and the shaft are related by this equation and the shear stress due to torsion. So the torque T is equal to the shear stress due to torsion multiplied by J over R. And we'll understand in a moment why or how we can use this equation. And the J, the polar moment of inertia of the cross-sectional area of the shaft, is pi multiplied by d to the power 4 over 32, considering that we have a solid shaft. So the thing is that here, if we, based on this equation, if you multiply the shear stress by J over R, this is equal to the torque. So in this equation here, again the Soderberg equation for torsional moment. So we have here a mean shear stress. We have here a reversed shear stress. So if we multiply the top and the bottom of this equation by J over R, so this mean shear stress multiplied by J over R is equal to the mean torque. And this value multiplied by J over R gives us the reverse torque that we have already. In this case, also see here, the endurance strength of the material in shear is equal to 0.5 times the endurance strength of the material based on bending. So if the endurance strength based on bending is given, multiply this value by 0.5, it is going to give you the endurance strength in shear. And the same applies for the yield strength. If the yield strength of the material based on tensile test is given, multiply this by 0.5, it gives you the shear strength of the material, or the yield strength of the material in shear. So this means that we're going to replace this value, the yield strength of the material in shear, by 0.5 is yield here in the numerator and denominator, and also the endurance strength of the material in shear is 0.5 times S, or the endurance strength based on the bending experiment. Right. So based on this equation, the factor of safety is given, and then we can rearrange this equation in order to find the diameter of the shaft. So if we consider J over R, because both of them are function of the diameter of the shaft, if we consider this is our unknown, so J over R is equal to this bracket multiplied by the factor of safety divided by 0.5 SCL, then the mean torque is being calculated as 2050. This value is 1. We don't have any notch in the shaft, any notches in this shaft. And then the yield strength is given, the endurance strength is given, and the reverse torque here is being calculated. So divided by the strength here, or the yield strength, over multiplied by 0.5 divided by 2, which is the factor of safety. So this 2 is obviously 0.5 here can be just used as 2 in the denominator. So this gives us the value for J over R, which is millimeter cubed. And then the J over R itself, based on this equation, going back to this equation, this is J. And then if you divide the left and the right hand sides by D over 2, which is the radius, so in this case, it is J here over D over 2 or multiplied by 2 over D. This is the same thing. So eventually this gives you pi multiplied by the diameter of the shaft cubed over 16. And this value here, which is J over 2, based on this equation, is equal to here 40,463.24. So if we equate this value here, which is pi over 16 times the diameter cubed, by this value we can find the diameter of the shaft, which could be considered as 60 mil. It's 59.066 mil, but we can consider this for ease of manufacturing as 60 mil. This is the end of problem number